Finding one of the short sides of a right triangle using Pythagorean Theorem is very simple, and of course it's very similar to using the Pythagorean Theorem to find the length of the hypotenuse. We take the formula, we plug in the length of two sides, and we simplify algebraically and we find the length of the missing side. There are a couple of slight differences, and let's take a look at a few examples. In this first right triangle I have a hypotenuse of 10 centimeters and a medium length side of 9 centimeters. I am going to call the 9 centimeter side my side A, but we could call it A or B. These are interchangeable, it wouldn't matter. And of course C in this form of Pythagorean Theorem is the variable that represents the hypotenuse, and that C will be replaced with this 10. A squared then becomes 9 squared, and C squared becomes 10 squared. If I square my 9 and my 10, I get 81 plus B squared equals 100. Now I want to isolate my variable. B squared stays where it is and will be equal to 100 minus 81. 100 minus 81 is 19. So B squared is equal to 19. B, the length of this side, is equal to the square root of 19, which is 4.36 if I round it to the nearest hundredth. And the unit of measure was centimeters, so it is 4.36 centimeters. We have found the length of this side. Over here I have another form of Pythagorean Theorem, where I have isolated my A squared by moving the B squared to the other side of the equals where it becomes negative. So I'm doing algebra before I plug any numbers into the formula. When I plug the numbers in, this time I'm going to make A squared my unknown. A will be the unknown side. C squared is going to be 10 squared again. And B squared this time is the 9 squared. The good thing about doing this is that my variable is already isolated on the left side, and I have a lot of simplifying that I can do on the right side. A squared is equal to 100 minus 81. A squared is equal to 19. A will be equal to the square root of 19, which of course is 4.36. Apply my unit of measure. So this is two different ways of using the same formula, and which way you like to do it is really up to the student. You should do whichever is most comfortable for you. Now let's look at another example where we have a right triangle with a hypotenuse of 20 meters in length, and one of the two shorter sides is 14 meters in length. We're going to find the other side, this side along the bottom. Another slight difference is this time I have used h as the variable to represent my hypotenuse. Sometimes Pythagorean Theorem has c representing the hypotenuse, sometimes it has h. No matter which variable is being used to represent the hypotenuse though, this is still Pythagorean Theorem, and the algebra is going to look the same when we simplify. I am going to make A equal to the 14 meter side this time, so A squared becomes 14 squared. B squared is my unknown and will represent the length of this side. And H squared is going to be 20 squared. 14 squared is 196, and 20 squared is 400. So doing some algebra, I get B squared is equal to 400 minus 196, which is 204. B therefore will be equal to the square root of 204, which is 14.28 if I round to the nearest hundredth. And because the unit of measure is meters, we have found a side length of 14.28 meters in this case. All of these examples really are the same. The only thing that is changing is which side do we want to call side A and which side do we want to call side B. It doesn't matter, they are interchangeable. And are we using a form of Pythagorean Theorem where the hypotenuse is represented with the letter C or the letter H? Again, it doesn't matter. Do we want to use this form of the Pythagorean Theorem, or do we want to do some algebra to that formula before we start plugging in numbers in order to isolate the variable that we want to isolate by the end of the problem anyway? This is a matter of personal choice. This is how you use Pythagorean Theorem to find missing sides that are not the hypotenuse in a right triangle.